Hello friends, my name is Tushar and today I'm going to talk about how to find articulation point in connected undirected graph using Tarjan's algorithm. So what is articulation point? Articulation point is a vertex in connected undirected graph such that removing that vertex will disconnect the graph. Let's look at a few examples. So in here I have a graph A, B, C. Here my articulation point is B because if I remove B, it disconnects A and C. In this example, my articulation point is D. If I remove D, I have three components left, A, B, C, E and F. And another articulation point is B. If I remove B, then I'm left with A, C and E, D, F. And in this example, my articulation point is C. If I remove C, I'm left with A, B and D, three different components. So one application of articulation point would be to find a single point of failures in a network and probably reinforce those nodes or vertices. So in the next section, let's see how to find articulation point in using Tarjan's algorithm. The way this algorithm works is that you have to find a back edge, and if there is a back edge, it means that there is another path to connect two vertices, so the current vertex cannot be an articulation point. Let me explain you with a quick example. So if I have three vertices, A, B and C, here A clearly is not an articulation point, C is clearly not an articulation point, but B is an articulation point because removing B will disconnect A and C. But if there was another edge, a back edge from A to C, at that point B is not an articulation point anymore because even if B is removed, then A and C is connected. So this algorithm is finding the presence of this back edges and ruling out a vertex to be an articulation point. So we need to do some bookkeeping for this algorithm. So one is visited set. It is going to store all the vertices which are visited till now in the DFS traversal. Then the time is the current visited time. This is a set articulation points storing all the articulation points that we have found till now. And then we'll need three map. One for storing the visited time, so visited time of a vertex. Second is a load time of a vertex. Load time of a vertex is the minimum of all the visited time of all the adjacent vertices which are reachable from a given vertex in the DFS traversal. And third is the parent of a given vertex in the DFS traversal. So a vertex is an articulation point if it satisfies any of these two conditions. One is if it's a root vertex with two independent children, then it's an articulation point. By independent, I mean that they are not connected to each other through any other means. So if we started from D, it has two children, C and E, and these vertices are not connected through any other means. So D is an articulation point. The other is if a visited time of a vertex is less than or equal to the load time of any adjacent vertex, then that vertex is again an articulation point. And this is what I was talking about, the back edge. So let's try to understand how this algorithm works with this example here. Let's say we started our DFS from D. So we put D in visited. The visited time of D will be this times 0, which is the numerator. The load time will be again 0, which is the denominator. And then the parent of D is null because D is the root of this DFS. And then it has at least one child C, so the count of the children will be 1. Then we go from D to C. Before going there, we'll increment our time, so time becomes 1. So C is not in visited, so we'll add C to visited. Then the visited time of C will be 1, which is numerator. The load time will also be 1, which is denominator. The parent of C will be D. Now we'll explore children of D. So first child explores children of C. So first child is D, but D is where C is coming from, so we'll ignore D altogether. Then next child we get is A. A is not in visited. So we'll add A to visited, we'll increment our time by 1, and so the visited time will be 2, low time will be 2, and parent will be C for A. Then we'll explore children of A. First child is C, and C is where A is coming from, so we ignore C. And then we go to B. B is not in visited, so we'll add B into visited. We'll increment our time, so this becomes 3. So the visited time is 3, low time is 3, parent is A. So for B, let's explore its children. So it's coming from A, so we'll ignore A. What about C? So C is already in visited, so this edge here, BC, is a back edge because this edge creates a cycle, and since C was already visited and C is not where B was coming from. So let's see if B is an articulation point. So B is clearly not the root vertex of this DFS because D's, so it doesn't satisfy its condition 1. And the visited time of B, which is 3, is not less than or equal to the low time of adjacent vertex, which is C. So low time of adjacent C is 1 and B is 3, and 3 is not less than or equal to 1. So B is not an articulation point. B is pretty much a corner vertex, and removing B is not going to disconnect this graph. So then, before going to A, we are going to update B's low time. So B's low time will be the minimum of whatever the current low time is 3, or the low time of its adjacent vertex, which is 1. So here we'll say 1. Then we'll go back to A. For A, it's clearly not the root vertex, and the visited time of A, which is 2, is not less than equal to the low time of its adjacent vertex, which is B, which is 1. So A is also not a articulation point. And the reason for that was because B has this back edge with C. It means that even if we remove A, B is still going to be connected to the rest of the graph. And the way we found out was when C propagated its visited time to B, which was 1, and then we checked this 1 against the visited time of 2, and 2 was not less than or equal to 1, which tells us that there must be a back edge from B to C, which connects B to the rest of the graph. If this edge did not exist, this edge B to C did not exist, in that case A would be an articulation point because removing A would disconnect B from rest of the graph. So A is not an articulation point, so we go back to C. C is clearly not the root vertex. Then visited time of C, which is 1. Before we go back to C, we'll update A's low time. A's low time will become 1, which is the minimum of its current low time, or B's low time. So 1. So going back to C, C doesn't satisfy 1. The visited time for 2, visited time of C, which is 1, is less than equal to the low time of adjacent vertex, which is also 1. So it means that C is an articulation point. Basically removing C is going to disconnect AB from rest of the graph. So C is clearly an articulation point. Then we explore other child of C, which is B, and B is already visited and C is already articulation point, so we do nothing about it. So then we go to D. So at D has another child E, and E is not in visited, so we'll add E to visited. And since that's another child, we'll increment the child count for D, which is now becomes 2. And then let's go to E. E has, and then increment over time, so this becomes 4. So for E, our visited time is 4, our low time is 4, and its parent is D. E has a parent D. E has child D, but D is where it is coming from, so we'll ignore D. E has another child F. So let's go to F. F is not in visited, so let's first add F in visited. Increment our time by 1, so this becomes 5. So visited time is 5, low time is 5, and this is, parent is E. So for F has child E, but E is where it is coming from, so we'll ignore E. Then F has another child G, and G is not in visited, so let's add G to visited and increment our time, so this becomes 6. So for G it's 6, 6 and F. So G has child F, but F it is coming from, so we'll ignore F. G has another child E, and E is already visited. So this edge here must be a back edge because E is already visited. So then at G it doesn't satisfy the first condition because it's not the root of DFS, and the visited time of G, which is 6, is not less than equal to the load time of E, which is 4. So G is not an articulation point. Also, before leaving G, we'll update its load time to be 4, which is the load time of E. So then we go back to F. So F, visited time at F is 5, which is not less than equal to the load time of its adjacent vertex G. So for G, F is not an articulation point, because even if you remove F, G is going to stay connected to rest of the graph through this edge here, back edge here. So let's first update F's load time, so this becomes 4, which is G's load time. But F has another child H, and let's go to H first. So we go to H and we increment our time, so this becomes 7. So this is 7, visited time is 7, load time is 7, it's coming from F. For H is coming from F, and we don't do anything about H. And so H is not an articulation point clearly. So now we come back to F. So what about F in respect to H? The visited time of F is 5. The load time of its adjacent vertex is 7. So this condition is true. So F is an articulation point. So as you can see, as long as your visited time is less than equal to any of the adjacent vertices load time, so in this case H, you will be an articulation point, because removing F is going to disconnect H from the rest of the graph. So then from F we go back to E. For E, this condition is not true. What about this condition? So the visited time of E, which is 4, is less than or equal to the load time of adjacent vertex, which is also 4. So this is true. So E is also an articulation point, because removing E is going to disconnect these 3 guys from rest of this graph. So then we are done. E has another child G, but G is already visited, so we do nothing and we come back, and E is already an articulation point. So from E we come back to D. So for D, we have done visited visiting all its vertices, all its adjacent vertices, and for D is a root vertex. It is, because its parent is null, and it has 2 independent children, at least 2 independent children, which is true because this count is 2. It means that D must also be an articulation point. So D is our final articulation point. And at this point, it concludes the algorithm, because we have explored all the childrens. So we have 4 articulation points in this graph: C, F, E, and D. Removing any of them is going to disconnect this graph. So the time complexity is pretty straightforward. All it does is a DFS. It has all this bookkeeping information, but the time complexity is the time complexity of DFS, which is E plus V. So in the next section, let's look at the code for this.
Let's understand the algorithm of finding articulation point with this relatively simple example. So we have a graph A, B, C, D. For bookkeeping, we have this set visited, which contains all the nodes, vertices which are visited in DFS. And then we have another set containing which will store all the articulation points. And then we have a visited time, which is the numerator of our, in the example I explained. And then load time is the denominator of our example. And then parent is going to store the parent of every vertex. So we start DFS from any random node. Let's say we started DFS from A. So we go into this function DFS. Here our vertex is A. Our time initially is 0. First thing we do is we add A to visited. Then we put visited time dot vertex and time. So our numerator is 0. And then low time dot put, so our denominator is also 0. And time plus plus, so time becomes 1. And then child count is initially 0. Remember, child count is only important for the root of the DFS, and in this case A is the root of the DFS, so child count is 0. And then articulation point is false for A initially. And then we start exploring neighbors of A. So the first neighbor we explore is B. So B is not the parent of A in the DFS, so we don't go into this if condition. So we come here. B is also not in visited, so we go into this if condition. Parent. So first thing we're going to do is mark A as a parent of B in the DFS, and then increase the child count on A by 1, so this becomes 1. And then we go into the recursion from with A as B as the new vertex. So we go to the top here, vertex here is B now. First thing we do is we add B to visited, and then we put visited time as A as 1. So numerator is 1, and then low time is also 1. And then we increment this time by 1, so time becomes 2. And child count is not important for B because B is not the root of the DFS. So articulation point is initially false. Then we again start going into this for loop. And in here, let's say the first adjacent vertex we get is A. So A is the parent of B in the DFS. So we go into this if condition, hit a continue directly, and go back to the top of the for loop and explore the next adjacent vertex. So the next vertex we get is C. C is not a parent, so we don't go into this if condition. Also, C is not visited, so we do go into this if condition. Let's mark C's parent as B, and then we increment the child count, which is not important for B. And then we go into the DFS with C as the vertex. So we again go into the DFS. Here the new vertex is C. So first thing we do is we add C to visited, and then we are going to put 2 as the visited time numerator, and low time is also 2. And then we increment the time, so time becomes 3. And then child count is not important for C. And then articulation point initially is false. Now let's explore neighbors of C. So the first neighbor we get is B, and B is the parent of C. So we go into this if condition, and then we hit continue directly, and then go back to the top of the for loop. And then let's say the next neighbor we get is D. So D is not the parent of C. So we don't go into this if condition. We come here. Also, D is not visited. So let's first put D's parent as C. Then we increment the child count for C, which is not important because C is not the root of the vertex. And then we go into the recursion with D as a vertex. So we come here. This time the vertex is D. We put D to visited. We mark visited time as 3 for D, and low time also as 3. Increment this time by 1, so this becomes 4. And then child count is 0. Child count is not important for D. Is articulation point is set false initially. And let's start exploring neighbors of D. So the first neighbor, the only neighbor D has is C, and C is also the parent of D. So it goes into this if condition, hits the continue, go back to the top of the for loop. Again, there is no more neighbors of D to be explored, so we don't break out of this for loop, come to this point here. Here we are going to check if at this point we're going to check if the vertex is eligible to be an articulation point or not. So there are two cases here. If your parent is null, basically if you're the root, or if your parent is not null. In this case, D is not the root, and its parent is not null. And also we never set its articulation points to be true. We never hit this point. Our articulation point was always false. So we don't go into this if condition, and D does not get added to the articulation point set. So then we are going to go back into the recursion where C is the vertex. So let's explore. So we go back to the recursion where C is a vertex. So let's explore. Let's continue from here. So the visited time of C, which is 2, is less than equal to the low time of adjacent, which was D, which is 3. So that is true. So articulation point is true for C, and then we set the articulation point as true for C, and then we go back to the top of the for loop, and we have one more neighbor to be explored for C, which is A. So we go here. A is not the parent of C. C is not coming from A, so we don't go into this if condition. If visited doesn't contains A, so visited actually contains A, so we don't go into this if condition but hit this else condition. In this else condition, all I'm saying is I'm setting the load time of C, either the current load time which it has or the visit time of A. So the visit time of A is 0 and the load time of C is 2, so the minimum of the two is 0. So the new load time of C is 0. Basically saying that it has this back edge from A. And then at this point, we go back to the top of the for loop. Now we have visited all the neighbors of C, which is A, B, and D. So we break out of this for loop, come to this point. Here, we don't go into this first part of the if condition because C's parent is not null. So we come here. So if C's parent is not null and his articulation point is true, remember we said this is articulation point true when we were comparing against D. So C is an articulation point, so we're going to add it to the articulation point. Clearly C is, if C goes out, then we divide the graph into two parts, A, B, and D. So clearly C is an articulation point. Next, when C is all done, we go back to the recursion where B was the vertex. So we come to this point here. So now we're going to check if the visited time of B, which is 1, less than or equal to the load time of C, which is 0. Load time of C was 0. And remember how the load time of C got to 0? Because it has this back edge from A. So the visited time of B, which is 1, is not less than or equal to the load time of C, which is 0. So we don't go into this if condition and we go into this else condition. So what happened here was, since there was this back edge from A to C, C has this connection back to A, which made its load time to be 0. And as a result of that, B could not become an articulation point. If this edge did not exist, in that case, B would have been an articulation point. But since this edge existed, B is not an articulation point. Then we go into this else condition and we're going to set the load time of B as either the current load time of B, which is 1, or the load time of adjacent, which is 0. So minimum of the two. So in this case, we set the load time of B to be 0. So then we go back to the top of the for loop, and and at this point B has explored both its neighbors. So we come here to this point, to this if condition. Here B's parent is not null, so this is not null, and we never set B's articulation points to be true. So is articulation point for true for B. So this was always false. So B is not an articulation point. So finally we are done with B, and we go back into the recursion where vertex was A. So here we come here. So let's look at this. So visited time of A, which is 0, is less than equal to the load time of B, which is 0. It is true. So we set the articulation point of A as true. Is articulation point true for A? Then we are going to explore another. So we're going to go to the top of the for loop. Another neighbor of A is C, and C is not where A was coming from, so we don't go into this if condition. And C is already visited, so we don't go into this if condition. Come here, and then we set the load time of A, either the minimum of its current load time, which is 0, or 2. So in this case, it continues to be 0. And then we are done with this for loop because A has explored both its neighbor. So what we're going to do is we're going to come to this point here. So now this is where this child count is very critical. So parent of A is null because A was the root of a DFS, but its child count is not greater than 2. Child count of A is 1. So this is why even though the is articulation point of A is true, it's still not an articulation point because removing A is not going to split the graph into multiple graphs. So it's not going to disconnect the graph. So this is where the child count is very important for the root vertex. If we had not maintained this child count for the root vertex, what would have happened is we would have thought that A is also an articulation point based on the fact that this is articulation point is set for A, and we would have incorrectly thought of A as an articulation point. But having this child count greater than 2 as a condition, we prevented that. So now A doesn't go into this if condition for A, and then we break out, and then we return from this function altogether, and then we just return the set of articulation points. So in this case, C is the only articulation point for this graph. Again, the runtime complexity for this algorithm is the runtime complexity of DFS, which is O of E plus V. And then the space complexity is equal to the total number of edges, the total number of vertices, so which is O of V. So that's all I have to talk about articulation point. Please like this video, comment on this video, share this video, check out my Facebook page, check out my GitHub link, github.com mission quiz interview wiki. Thanks again for watching this video.